We now want to move on and look at IC current biasing, and we're going to talk briefly about current sources, current mirrors, and current steering circuits. So some of this you've already seen before, certainly a basic current source. We're going to use the MOSFET as our sample device, but this is applicable equally to bipolar transistors. Here I've drawn on the left a basic biasing current source and labeled the current flowing through the drain resistor as Iref. We've tied the drain of the MOSFET M1 to the gate, and so therefore VDG is equal to 0, and so the device is always in saturation, assuming that VDD is greater than 0. And the operating point can be determined as follows. If we draw a load line, and we have on the vertical, we have current, and our load line would have an intercept, a y-intercept of VDD over RD, and then it would have an x-intercept of VDD. If we plot the drain to source voltage here, we would have, drain to source voltage, which is equal to the gate to source voltage in this case, because they're tied together. We would have our square law curve here, which is expressed as Kn1, so that's our transconductance coefficient, divided by 2 times VGS minus V threshold squared. All right, and the intercept here is the operating point. That's going to be our Iref. So I've rewritten that right here. You get a quadratic equation. You can solve for it and find that Iref will be a function of VDD, RD, the transconductance coefficient, and the threshold voltage. So however you come by this, you're eventually going to have a current that is flowing through this transistor. Now the way that you use this to produce a current source is, or to produce a current mirror, then is that you connect another transistor, M2, to the same source potential as M1, and then you tie their gates together. So VGS2 is equal to VGS1, and of course that's equal to V threshold plus the square root of 2 Iref over Kn1. And if these transistors are identical, then the current that results right here, I0, is going to be equal to Iref. So let's evaluate this. I0, assuming that we're in saturation, so that means that this voltage VO here would have to be greater than minus a gate voltage, greater than VG minus the threshold voltage. The current I0 will be equal to Kn2 over 2 times VGS2, but VGS2, so we'll go ahead and write it, VGS2 minus V threshold. We're going to assume they have the same threshold voltage. This is simply going to be equal to this term right here, square root of 2I ref over Kn1, and so this all evaluates to Kn2 over Kn1 times I ref. Now we can write Kn1 as being equal to Kn prime times the width of transistor M1 divided by the channel length of transistor M1. Kn prime has to do with the mobility, electron mobility in the end material, and has to do with the capacitance of the oxide layer. So those are parameters due to the process. Okay, so they're common for all the transistors on this IC, but every transistor can be built to a different size. We can make a different channel width, we can make a different channel length. And so this becomes handy because now we can do the same for KN2, and now we can say that I0 is equal to omega, or W2 over L2 divided by omega 1 divided by L1 times Iref. So therefore, Iref can be scaled. Imagine that I0 had to be a milliamp. Well, you wouldn't have to waste another milliamp of current in your Iref. You could have a tenth of a milliamp. And then you could just simply make transistor M2 have a width 10 times greater than the width of W1 of transistor 1, keeping the lengths the same. So this allows you to produce scaled current mirrors throughout your IC. Okay, what we've looked at so far is really a basic current source. I think I called it a current mirror before, but it's a MOSFET current source. So we have this current source now, I0, that we can make use of for biasing an amplifier, etc. Now let's take that idea and let's consider how we can multiply its usefulness by creating a basic current mirror. So here we have a basic MOSFET current mirror. So we're just abstracting and saying we have a current source, Iref. Don't know where it came from, but we have that. And now we want to mirror it to somewhere else in the circuit. Well, we use the same gate source connected M1, M2 transistor arrangement. And now we can have this current I0, drain current through M2, being proportional to the reference current that we've produced elsewhere in the IC. And again, that output current I0 can be scaled, a scaled version of Iref, simply by scaling the geometries of these two transistors. Here I've shown to the right how one might implement or combine the basic current source that we just discussed with the basic current mirror presented here. And so I've drawn the a p-channel version. So these are two p-channel FETs, but this is the same current source as we saw right here, just reflected or to the VDD supply side. And so now we have a current supply of Iref, which is behaving just like that Iref current source. We're ignoring RO, output resistance, and that sort of thing right now. That all comes into play as well when you get into the details. But the essence of the circuit is that you can create a current source this way, and then you can mirror that current using the M1 and M2 here. And this can be expanded throughout your IC. So typically an integrated circuit will have multiple amplifier stages, and you'll need biasing for each of those stages. So once you have one current source, Iref, you can then mirror that multiple times. And here in this circuit, I'm showing 4 different replications. So we have I2, we have I3. These are both considered, technically we'd say these are current sinks. And then we would have I6 and I7, which are current sources. And notice that this stage right here is for level shifting, or referencing from going from ground referenced current source to a supply referenced current source. So M4 will have a current I4 flowing down, but that ends up being the same current, or I5 current will be the same as I4, and so now we can use the gate to source voltage of M5, which is a P channel, and apply that across the gate to source of M6 and M7, and now those transistors will supply currents I6 and I7, and those will all be related by the geometry scaling factors all the way back to IREF. This replication or scaling of IREF throughout a multi-staged amplifier circuit is what we call current steering. So we're steering the currents I2, I3, I6, I7 all by way of a reference current, IREF. Now let's consider some current sources, mirrors, and current steering circuits using BJTs. Much of this will be the same as for MOSFETs, but the big difference, of course, is that unlike the MOSFET, the controlling terminal, that is the base, does have some current flowing into it, and so that will affect how well the current reference is replicated or matched at the output of the current source. So here we have a basic current mirror, BJT-based current mirror, where we've tied the collector and base of Q1 together, and then we've connected the two bases together. And some simple analysis, just doing some KCL, leads us to the relationship for I/O in terms of IREF. And primarily what is happening here that results in I/O being less than IREF is that some of IREF actually flows down through this branch here and splits, supplying the two bases. And the amount of current that is lost, if you will, from IREF is going to be 2 times, because it's 2 paths, IC over beta. So that amount of current will actually be taken from IREF. So we can actually say that, well, the analysis is over here, and you can follow that, pause the video if you want to look at it. But the result is that I/O is approximately, we could write this as 1 plus 2 over beta. So if beta is 100, we're at about 2% error. All right, so 98% roughly of IREF is what we see at I out. Now, we can scale the currents like we did for the MOSFETs here. Instead of scaling the width and the length of the channel, we're going to scale the emitter base junction area. So we can have a scale factor that we'll define as M here, and it's the ratio of the area of the base emitter junction of Q2 to the base emitter junction of Q1. And that will ideally lead to an I out that is M times IREF. When we do that, if you go through the analysis again, we'll find that I/O is equal to this scaled version of IREF. And just to see the effect of having an M that is other than 1, see here in this case, the first example, M would be equal to 1. If we were to say that M was equal to 3, then I/O would be 3 times 3 over 1 plus 4 over beta. In other words, if beta was 100, then we would have approximately, roughly, a 4% error compared to a 2% error. So the more current gain we want, or current scaling we want, the more error there is. Now, just like for the MOSFET transistor or MOSFET mirror, there's an output resistance RO, and it's going to be equal to RO2 in this case. That's just the output resistance of this transistor Q2, and it will be equal to VA over IC, the collector current of Q2, which is approximately the early voltage VA over Iref. Now let's look at a typical current source. Just like the MOSFET current source, one simple type of source is just to use a resistor R, and here we would have a current flowing through R that would be approximately VCC minus the VBE junction of Q1, all divided by R. This will give us an output current IO that's approximately Iref over 1 plus 2 over beta, and an output resistance of RO2, where RO2 is the small signal output resistance of Q2. Now we can implement current steering with BJTs, and here's an example. One of the things that we can do that's a little different is that within one current reference branch, we can place an PNP and an NPN transistor and produce the two reference voltages. I guess we could have done that for the MOS as well. Come to think of it, we could have done this. Yeah, so we could have done that as well for the MOSFET implementation. So nothing unique here for the BJT. Okay, I think that's probably sufficient. This is all covered in section 7.4.3.